So in this class, we will be talking about Euler equations. Euler equations are kind of a special differential equation. It's second order differential equation, as you can see here. The difference in here is our coefficients are not constants. As you can see, the coefficients, the second order terms coefficient is the second order polynomial. First order terms coefficient is first order polynomial, and constant is the y terms coefficient. So this is the Euler's equation, at square y second derivative plus bt y first derivative plus cy equals 0. And in this one, instead of looking for the exponential solution, we will be looking for the power function solution. So you know that for the constant coefficient differential equations, we will be looking for e to the rt kind of solutions. But this time we will be looking for t to the r power function solution, okay? If that's the solution, now I can take the first and second derivative plugged in inside my differential equation, and just as we did for the exponential solution, if you simplify all the function and take the t to the r out, you will have the characteristic equation for Euler's equation. So characteristic equation for Euler's equation is ar r minus 1. So ar r minus 1. A is staying here as a coefficient of the second order term. R times r minus 1 is coming as the second order term power. And for the first order term, it is again br plus c. So just the second order term, you are taking a r times r minus 1. And if you open this characteristic equation, you can see that this is also a second order polynomial equation, which you can find the roots of this equation with the quadratic formula, just as we were doing for the characteristic equations before. So the same thing. For example, this is the Euler's equation, t square y second derivative minus 4ty derivative plus 4y equals 0. As you can see, a is 1, b is minus 4, c is 4. So I can write the characteristic equation, a is 1, r times r minus 1 minus b is 4, 4r plus 4 equals 0. And if you distribute this r, this will be r square minus r. There will be minus 4r here. That's why we have minus 5r plus 4. And you can factor this one and factor this equation out, and you can find the roots as 1 and 4. Okay? So until here, it's same. What you need to be careful about is writing the characteristic equation for Euler's equation. So this is not r square minus 4r plus 4. Instead of that, r times r minus 1 minus 4r plus 4. Okay? And you can write this, since these are the roots and since our solution is in the form of the power function t to the r, I'm writing 1 and 4 as the power and take the linear combination as the general solution. So c1t to the 1 plus c2t to the 4 is the solution. And you know that to be able to say that they form a fundamental set of solutions, we are checking the Wronskian. So t and t to the 4, take the derivatives, find the determinant. 3t to the 4 is not 0 if t is not 0. So this is the Wronskian also. And another way is, instead of finding the real and repeated roots, we can find, real and distinct roots, we can find real and repeated roots. This is example for that. Again, a is 1, t square y second derivative, 3ty derivative plus 4y. As you can see, t is bigger than 0. And if we let y equals t to the r, the characteristic equation will be r times r minus 1 minus 3r plus 4 equals 0, right? And if you open this one, this is the function we have. And if we factor this one out, we can see that 2 is coming twice as a root for this characteristic equation. So one solution is t square. What is the other solution? So you remember this answer of this problem. If you know one solution, how can you find the second solution? You can apply reduction of order. So we are looking for y2 as u times y1. y1 is the t square because r is 2 and our solution is in the t to the r form. And if that's t square, then you are taking the derivatives, you are plugged in inside your differential equation, and you can solve, you can reduce the order of the remaining, the resulted differential equation by assuming u prime is v. We already covered that up, remember that. And the derivative of v will be u second derivative. Then t v derivative minus v equals 0. And this is the first order differential equation. You know how to solve it. You can solve it with, I don't know, linear equation or separable equation. It depends on you, because this can be solved with two of it. And here you can find the u as c1 ln t plus c2. And if you write, since t square was the other solution, you can see that the second solution is t square ln t. So remember that for the constant coefficients differential equations, if we have real repeated roots, if one of them was e to the rt, the other one was t times e to the rt. In this one, if one of them is t to the r, other one is t to the r times ln t. So instead of t, it's coming ln t as a coefficient for the second solution. Okay, I will summarize the results in a table a little bit later, but let's look at the complex conjugate solution. This is another example for the complex conjugate solution. Again, we are writing the characteristic equation r times r minus 1 plus 3r plus 5. If you open that and solve to find the roots, you will see that the roots are minus 1 plus or minus 2i, alpha plus or minus beta I, let's say. And again, we are using the Euler's identity to turn this one into a solution. And you will see that here, the solution is t to the alpha cosine beta ln t, t to the alpha sine beta ln t. Okay, so the real part is coming as a power of t. The imaginary part is coming as a coefficient of cosine and sine, but with ln t. Not cosine 2t, it will be cosine 2 ln t. Okay, this is three different ways of the Euler's equation. Again, let's summarize. We have an Euler's equation. This is the form of the Euler's equation. And the solution is in the form of power function t to the r. And the characteristic equation is a r times r minus 1 br plus c. And if you find distinct real roots for this characteristic equation, you are writing the solution as t to the r1, t to the r2, and the general solution is the linear combinations of them. If you have real and repeated roots, one of the solution will be t to the r, another one is t to the r ln t. ln t is coming. We found this one by reduction of order. And if you have complex conjugate roots, then the solutions are t to the alpha cosine beta ln t plus t to the alpha sine beta ln t. Okay, this table is summarizing all the solutions of Euler's equation, and I will upload different examples for this section also in LMS. Okay, bye.